तो कल जो है हमने मैंने आपको दिखाया था कि if x star is a locally compact T2 space and boldface be its Borel sigma algebra, then for every measure, in fact it should be a completely regular Borel measure, then for every regular Borel measure actually हमारी assumption यही थी, regularity and Borel, then for every regular Borel measure mu from boldface B into 0 infinity, there exists this, in fact I should write like this, for each regular Borel measure mu from boldface B into 0 infinity, there exists a closed set. There exists a closed set E, and this closed set will be unique. Exists and exists uniquely. This will be uniquely determined. Such that the measure of the complement of E will be 0, and second, measure of E intersected with V will be positive whenever V belongs to tau and V intersection with E is not phi. ठीक, और ये जो सेट है इसको हम कहते हैं एक्चुअली द सपोर्ट, ये मैंने कल ही आपको बताया था, दिस सेट E इज कॉल्ड द सपोर्ट ऑफ म्यू. सो बेसिकली मैं आपको दिखा रहा हूँ यहाँ के दैट ये हमने कल प्रूव किया था, एवरी रेगुलर बोरल मेजर ऑन अ लोकली कॉम्पैक्ट T2 स्पेस हैज़ अ सपोर्ट. ठीक, I will consider some remarks. I will be examining certain remarks now. First we'll examine the scenario. If the support will be denoting the support of measure mu of a regular Borel measure defined on a locally compact T2 space, will denote this support by this symbol sup, SUPP of mu, SUPP mu. First we'll examine this case. If this sup mu is phi, if the support is an empty set, तो इस केस में आप मुझे क्या बता सकते हैं? What can you tell me about this mu then, if the support is phi? If the support is an empty set. Well, we know that if E is the support, then the measure of its complement is 0. So if phi is the support, then measure of the complement of phi will be 0. And what is complement of phi? That's x. So in this case, actually, measure of x will be 0. then mu of x, which is the complement of phi, will be 0, and therefore this mu has to be the zero measure, and therefore this mu is the zero measure. And conversely also, if mu is the zero measure, then support of mu will be the empty set. So converse is also true. If mu is the zero measure, then its support is the empty set. So this is basically if and only if. ठीक? So this is first scenario. So it's not interesting. अगर देखा जाए ये कोई interesting scenario नहीं है फिर, because in this case this measure turns out to be the zero measure. So ये कोई interesting situation नहीं है. Now we'll examine this scenario. If the support of mu is x, इस केस में it's actually a interesting situation. ये तो आपने देखा, this is not interesting, because यहाँ the measure, it turns out to be the zero measure. However, when it comes to this case, where the support is x, the underlying set, in this case we actually have some nice things. यहाँ कुछ अच्छी चीज़ें होती हैं. अब एक चीज़ मैं आपको यहाँ दिखाऊंगा. You consider this situation. आप क्या करिए, you assume x star is a locally compact T2 space, bold face B its Borel sigma algebra, and mu from boldface B into 0 infinity be a regular Borel measure. With support mu equal to x. So let's observe this scenario. इसके बाद आप क्या करिए, let f and g be two continuous. Yeah, actually I'll write like this. इस तरह से लिखेंगे हम. Let f from x into r and g from x into r be two continuous functions. Be two continuous functions over this topological space. They are real valued functions, by the way, over the topological space x star. Okay, ये आप assume करिए. Suppose we are assuming that f and g are continuous functions over this topological space. We further assume this. Assume these two functions f, they disagree at a point. At some point, कोई point है in x where the functions are disagreeing. That means fx is not equal to gx. Okay. Where this x is some point in capital X. कोई point है capital X में जहाँ ये f और g agree नहीं करते. Full stop. Now if we consider this function h, define it as f minus g. First we can speak about the difference, because f and g are real valued functions. So I can speak about their difference also, because you can speak about the difference of two real numbers. ठीक? So we can speak about the difference of the images, f image and g image. So therefore we can speak about this h. And this h, it will actually be a continuous function. If h be equal to f minus g, then this h will be a continuous function. Then this h, it will be a continuous function from x into r, because it's actually a difference of two continuous functions. Then f from x to r is h from x to r is a continuous function. और इस x पे since fx is not equal to gx, so therefore h at this x, this will be not 0. Right? So it will be not 0. So either now यहाँ दो possibilities है, या तो h positive होगा या negative होगा, because h is real valued. So h of x जो है, it will be either positive or negative. So h of x is either positive or h of x is negative. We'll assume that hx is positive. और अगर ऐसा नहीं है, if hx is negative, in that case हम क्या करेंगे, we'll take h as g minus f. Instead of f minus g, we'll take h as g minus f. So we can ensure that this h is positive. Okay, so we may assume without loss of generality that this h is positive. अगर ये negative है, in that case, instead of taking h as f minus g, will take it as g minus f. So h will be positive at x. So without loss of generality, we may assume hx is positive. So it will be like this. Suppose this is 0 और hx इसके right में होगा. अब इसके बाद आप क्या करिए, you pick an epsilon greater than hx. कोई number आप pick करिए greater than hx. Let's pick an epsilon. It can be done. hx is positive और इसके बाद आप एक epsilon pick करिए. So pick an epsilon greater than h of x. फिर आप ये देखिए, then O equal the open interval. O is going to be an open interval और इसका जो left end point होगा, it will be 0, और जो right end point होगा इसका, it will be epsilon. Then O equal to this 0 to epsilon. This being an open interval is clearly open and it contains h of x. Then O equal to this is open in R because it's an open interval with, और इसमें ये भी है, ये जो h of x है, it's a point in O. ठीक है? Now that O is open in R and h, we know that it's a function, it's a continuous function from x into R. H is continuous, so it must be pulling open sets back to open sets. So if we speak about the inverse image of O under H, this, it will be open in X star. That means it will be in the topology. It will be in ta. And what is H inverse O actually? It's actually the set of all those x's in X whose image goes to O. Since the H image of X is also going to O, so this X, it will be in H inverse O. So that means this H inverse O is because it contains X, so therefore it becomes a non-empty open set. ठीक, हम ये जो H inverse O है इसको हम V से denote करेंगे. So let's denote this by V. Then this V is non-empty and open. And what is my support in this case? We are assuming that the support is X. So in this case, the E जो आप ऊपर वाली theorem में देख रहे हैं, it's actually X. So E in this case is X. Now clearly अगर आप देखेंगे, if you take a look at this V intersected with E, where E is the support of mu, since in this case the support is X, so therefore this will be actually V intersected with X, and V intersected with X is is V. V intersected with X is V, and V is non-empty, so this is not phi. So that means this V is non-empty and it intersects, it has a non-empty intersection with the support. So that means what? That means इसका जो mu होगा, mu of V, it will be positive. ठीक? So it will be positive. Now what is V actually? V is actually H inverse of O. So this actually means H inverse of O, इसका जो measure होगा, that will be positive. Now what is H inverse O? H inverse O by definition is H inverse O जो है, by definition it's actually the set of all those x's in I should write something else because x जो है ना हम किसी और चीज़ के लिए इस्तेमाल कर रहे हैं, so I'll be using u. So it's actually the set of all those u's in x such that h of u, it belongs to O. And what is O? O is the open interval 0 to epsilon, right? और इसका जो मेजर है, दिस इज पॉजिटिव, जो आपने ऊपर यहाँ देखा. So that means what? This means mu of, ये यहाँ कुछ से कुछ एक इंटरेस्टिंग चीज़ निकलने जा रही है, तो I suggest you to pay close attention to this. So this is mu of all those u's in x such that h of u belongs to this. So that means h of u is positive and less than epsilon. ठीक है? And this is positive. The measure of this set is positive. Now you keep in mind this information. This set has positive measure. And in view of this information, अब मुझे आप ये बताइए, if you take a look at this, the set of all those u's in x such that f of u is not equal to g of u, ये सेटअप लीजिए और दूसरा ये सेटअप लीजिए, set of all those u's in x such that 0 is less than f of u minus g of u is less than epsilon. में से कोई मुझे बता सकता है what is the relationship between these two sets? इन सेट्स के दरमियान एक रिलेशन है, कोई बता सकता है आप में से what is the relation? If you pick a point in this set, उस पॉइंट के लिए क्या होगा? f minus g when evaluated at that point will be a positive number. That means f और g बराबर नहीं होंगे. So that means वो पॉइंट फिर यहाँ भी होगा. So that means the relation is this. It's a subset of this. What is fu minus gu? It is h of u, because this is how we have defined this. So this set is actually this set. और इस सेट का मेजर पॉजिटिव है. दिस सेट इज कंटेनड इन दिस सेट, सो दैट मीन्स इस सेट का भी मेजर पॉजिटिव ही होगा. ठीक है, तो बेसिकली हम यही अब कंक्लूड कर सकते हैं. यू कैन कंक्लूड दिस, द मेजर म्यू मेजर ऑफ दिस सेट the measure of this set is positive. So that means what? That means f is not equal to g almost everywhere. You cannot say this. Actually you cannot say that f is equal to g AE, because for this thing to happen the measure of this set should be 0, but आप यहाँ देख रहे हैं कि the measure of this set is positive. So that means this is not true. F is equal to g AE. This is not true. So what is the moral of the story? The moral of the story is, even if these two functions f and g they disagree at a single point, then we cannot have this. We cannot have f and g to be AE equal. ठीक है? So that means what? That means if f and g are equal AE, then they should be actually equal. यहाँ exceptional points नहीं हो सकते, because यहाँ मैं आपको basically वही दिखा रहा हूँ, occurrence of a single exceptional point. Even if there is a single point where f and g are not equal, then you can show that the measure of this set, the measure of this set is positive, and that means f equal to g AE cannot happen. ये चीज़ नहीं हो सकती फिर. So if you want this thing to be true, then f must be equal to g. So basically मैं आपको यही दिखा रहा हूँ. If f is equal to g AE, it actually implies f is equal to g. And converse is obviously true. So यहाँ ये एक interesting चीज़ होती है. If you have a locally compact T2 space and mu is a regular Borel measure on that space, then two continuous functions are equal AE if and only if they are equal. ठीक? But provided the support of the measure is x. ये चीज़ आप इसमें आप इस चीज़ का इस्तेमाल कर रहे हैं. The support is x. तो यही चीज़ को हम ना पॉइंट आउट करके लिखेंगे. जो मैं आपको दिखा रहा हूँ, इसी चीज़ को आप नोट करके रखिएगा. So moral of the story is this: if mu is a regular Borel measure, on a locally compact T2 space with support of mu, locally compact T2 space x आप यहाँ लिखिएगा. with support of mu equal to x, then any two continuous functions on x are equal almost everywhere if and only if they are equal everywhere. ठीक है, तो ये होता है in these spaces. अब ये भी पता है that the R with the Lebesgue measure is if you take R with the Lebesgue measure, in the first place R is locally compact T2 space and Lebesgue measure is a regular Borel measure on R. So whatever we have, whatever you are seeing here is also true for R then. So ये चीज़ R में भी होगी फिर. So it's actually a remarkable property of continuous functions in R. Any two continuous functions on R are equal AE if and only if they are equal everywhere. So basically for continuous functions in R, AE equality means equality and equality already means AE equality, so they are equivalent. और इसका रीज़न एक्चुअली ये है बिकॉज इट्स एक्चुअली ट्रू इन मोर जनरल सेटिंग्स और वो जनरल सेटिंग्स ये है locally compact T2 space, mu is a regular Borel measure, then two continuous functions are equal AE if and only if they are equal everywhere. ये एक important property है of these spaces. But इसमें यह है कि ये ना इसमें एक्चुअली मैं फिर से reiterate कर रहा हूँ, this thing plays a pivotal role. ये तभी आप claim कर सकते हैं when the support of your measure is the whole space. क्योंकि Lebesgue measure का सपोर्ट जो है ना इट्स ऑल्सो आर, तो एक्चुअली इसीलिए वहाँ भी ये चीज़ आपको देखने को मिलेगी. टू कंटिन्यूस फंक्शंस ऑन आर आर इक्वल AE इफ एंड ओनली इफ दे आर इक्वल एवरीवेयर. ठीक है, तो ये बात है. इसके बाद आप अब ये एक ना रिमार्क आप रिकॉर्ड करी है. इट्स एक्चुअली एन ऑब्जर्वेशन एंड दिस ऑब्जर्वेशन विल एक्चुअली बी अ motivation for our next definition. इसमें आप क्या करिए, let x be equal to r. Let x be equal to r and S the semiring be the collection of closed open intervals a b such that a and b vary over r. ऐसे लिखिएगा आप, x इक्वल टू r कॉमा करके लिखेंगे, कॉमा s be equal to this and mu the measure be equal to the length function. एक सेकेंड. Mu be the length function, mu be equal length function on S. ठीक है, then this triplet RS mu, we know that it's a measure space. This is a measure space, right? Now you consider this function. You consider f from x to r defined by this rule. Fx is defined as x square for all x's in R. Now clearly this function is continuous. It's a continuous function. Now my question to you is this function an integrable function? The answer to this question is actually no. This function is not an integrable function over this measured space. Although it's a continuous function, but it's not an integrable function. Because we know that integrals are finite quantities. और अगर इसको आप integrate करने बैठेंगे आपको कोई finite quantity नहीं मिलेगी. ठीक है? So although the function is continuous, but it is not an integrable function. So that means not every continuous function is an integrable function. Generally speaking, not every continuous function is an integrable function. This function is not integrable with respect to the Lebesgue measure. So the moral of the story is this: not every continuous function is an integrable function. हालांकि यह फंक्शन में कोई प्रॉब्लम नहीं है. अगर प्रॉब्लम है वो असल में मेजर स्पेस में है, because it's an infinite measured space. If you go for mu star x, it will be infinity. This actually causes problems. The infiniteness of the measured space. Okay, so it's because of this reason that this function fails to be an integrable function. Although it's a continuous function, but it's not integrable. So this is the moral of the story. Not every continuous function is an integrable function. Generally speaking, अगर ना वो abstract settings में आप है तो not every continuous function is integrable. Now the question is, which continuous functions are integrable? And the answer is, और यहाँ भी ना ये कुछ technicalities हैं. You should be dealing with a locally compact T2 space. The measure should be a regular Borel measure. अगर ये चीज़ें हैं तो I can give you an answer to this question at which continuous functions are integrable. And the answer is all continuous functions with compact support. But first I must tell you what is this support of a continuous function. तो मैं पहले आपको वही बता रहा हूँ. So you record this as a definition. Let X star be a topological space and f from x into R be a function. Then the support of this function f, this is the general definition. हम support किसे कहते हैं? Support of a function किस चीज़ को कहते हैं? ये उसकी definition है. Then support of f denoted by, इसके लिए जो हम symbol इस्तेमाल करते हैं, it's this sup f is defined as, it's defined like this: sup of f It is defined as, ये ध्यान से देखिएगा कि मैं क्या कर रहा हूँ. First you have to identify all those x's in x where the function f is not 0. You have to identify all those points where the function is not 0. और उन सारे पॉइंट्स को आपने कलेक्ट करना है. ऐसा करने से आपको एक सेट मिलेगा और उसी सेट का आपने क्लोजर लेना है. द क्लोजर ऑफ दिस सेट, ये जो बार है, दिस बार डिनोट्स द क्लोजर. ठीक है, जब आप क्लोजर लेंगे you'll get a क्लोजर सेट और उसी क्लोजर सेट को हम कहते हैं सपोर्ट ऑफ एफ. दिस इज हाउ वी डिफाइन सपोर्ट. ठीक है. Now you imagine या you consider this scenario. ये आप as a remark लिखेंगे. Let x star be a locally compact T2 space, comma, mu from, या पहले ऐसे लिखिएगा, locally compact T2 space, boldface B its Borel sigma algebra, and mu from boldface B into 0 infinity be a regular Borel measure. Regular Borel measure. Full stop. Assume f from x into R is a continuous function, with compact support, and let's suppose the support of this function f is k. So k जो है ना, यहाँ मैं denote कर रहा हूँ to denote, I'm using this k to denote the support of this continuous function. Then पहली चीज आप यहाँ नोट करिए, what will be mu of k? What is k? K is the support of this function, और यहाँ assume कर रहे हैं हम कि the support is compact. What will be mu of k? मैं आपसे कह रहा हूँ it will be a finite quantity, और आप मुझे इसका reason बताएंगे. बताइए, what is the reason for this? बता सकते हैं आप में से इसका रीज़न कोई? इसका रीज़न ये है, द मेजर इज़ अ रेगुलर बोरल मेजर. वो डेफिनेशन आप देखिए, हम कब कहते हैं मेजर को दैट इट्स अ बोरल मेजर. So it's actually this thing, because the reason is this, because mu is a regular Borel measure. This is the reason that mu of k is a finite quantity. ये एक चीज़ है. दूसरी चीज़, if you pick a point x outside k, that means x lies in the complement of k, then x जो है, it does not belong to k. And what is k? K is actually the support. And what is support? Support is all those u's in x such that fx is not 0. ये set आपने लेना है, फिर इसका closure. So x is not in the closure of this set. So if it is not in the closure, so therefore it cannot be in the set either. So that means what? And therefore ये x जो है, ये इस सेट, चूँकि ये इस सेट के क्लोजर में नहीं है, तो ये सेट में भी नहीं हो सकता. सेट में नहीं होने का मतलब है कि ये चीज़ इस x के लिए, सॉरी मैं यहाँ ना प्रॉब्लम सही से नहीं लिख रहा हूँ इस चीज़ को. So I should be writing like this: all those u's in x such that f of u is not 0, because this is the support. The closure of this set is the support. X is not in support. It means what? It means x is not in the set, this set. So that means if you take the value of f at x, it will be 0. So outside support, the functions, every function value is, if you take a point outside the support, the function value at that point will be 0. ठीक है? So I can actually now write this f as, ये ध्यान से देखिएगा, I can write this f in view of this observation, because outside this k the function is 0. So I can write this f as f times chi sub k, where chi is the characteristic function. In view of this observation, this thing makes sense. If you take f times chi sub k, it will be actually f. Because outside k this will be 0, and so is this function. So outside k we have equality, or inside k also we have equality, because inside k this thing will be 1. Chi sub k will be 1. Okay? So f can be written like this. So, and what this essentially does, it actually in a way is restricting the function f to k. And what is k? K is a compact set. And what is the function? It's a continuous function. It's a continuous real valued function. And we know that a basically इसका reason ये है. If you actually, असल में आप इसको ऐसे देखिए, if you evaluate f at each point of k, that means if you consider this f of k, k being compact, so this will also be compact. और ये compact कहाँ होगा? In R. And compact in R means closed and bounded by Heine-Borel theorem. Closed and bounded. Now bounded means what? Bounded means it has a lower bound and it has an upper bound. And closed means it contains all the limit points. And we know that the sup and the inf, जो है ना, ये चीज़ मैंने एक्चुअली जब मैं आपको टोपोलॉजी पढ़ा रहा था उस टाइम मैंने ये चीज़ें आपके साथ डिस्कस करी थी. Bounded means this fk has an infimum as well as a supremum, and closed means वो inf और ये वो sup fk में ही होने चाहिए. So that means this fk attains its bounds. It has a minimum value, it has a maximum value. ठीक है? या आप ऐसे भी इसको आप देख सकते हैं, since this fk is closed and bounded, so therefore obviously this, if you are restricting yourself to k, this function f will be a bounded function. So that means modulus of f of x it will be less than or equal some m, and this will be true for all the x's in k. ठीक, यही चीज़ को आप यहाँ अगर ये इंफॉर्मेशन को अगर आप यहाँ इनकॉर्पोरेट करेंगे तो आपको क्या मिलेगा. देखिए कैसे आप इसको इनकॉर्पोरेट करेंगे. यहाँ आप यहाँ से देख रहे हैं, ऊपर आप देख रहे हैं कि दैट f इज इक्वल टू f टाइम्स chi sub k. So mod f will be equal modulus of f times modulus of chi sub k. ठीक, and this will be obviously less than or equal to m times chi sub k. I can release this chi sub k from the modulus because it's a non-negative function. ठीक है, एंड मॉडुलस बीइंग नॉन नेगेटिव तो मैं एक्चुअली ऐसे लिख सकता हूँ. So 0 is less than or equal to mod f is less than or equal to m times chi sub k. Now what is m times chi sub k? आप recall करिए, this k it's a set, it's a compact set. So that means this lies in the, you are in a T2 space. Compact sets are closer, and otherwise also this k जो है ना, because it's the support and support is closer, so it's a Borel set. So therefore it's a measurable set. So therefore this is a measurable function, and this k has finite measure. So therefore m times chi sub k is a stub function. Stub function means it's an integrable function. This is integrable. So ये कौन सी situation है फिर? It's a scenario where this function f is squeezed between two integrable functions, because 0 is also integrable. Now what is this f? F is continuous. So that means it will be pulling open sets. If you take inverse image of an open set under f, this will be open. Open means it will be in tau. If it is in tau, it must be in the Borel sigma algebra. और Borel sigma algebra में होने का मतलब है it's measurable. So f pulls open sets back to measurable sets, because it actually pulls open sets back to open sets, because it's a continuous function. And since every open set in this case is measurable, because यहाँ जो आपका simmering है, it is the Borel sigma algebra of this topology. So it is for this reason that this f is also a measurable function. So it's a scenario where this measurable function is squeezed between two integrable functions. So therefore it must be integrable. और ये पूरे डिस्कशन में ये जो f हमने लिया था, what is this f? We assumed about this f that it's a continuous function with compact support. So the moral of the story is every continuous function with compact support is an integrable function. ऊपर आपने देखा not every continuous function is integrable, but when it comes to continuous functions with compact support, they are integrable, and these are the details. So every continuous function with compact support is an integrable function. ठीक है, अब इसके बाद आप एक नोटेशन रिकॉर्ड करें. Let x star be a locally compact T2 space, boldface B be its Borel sigma algebra, and mu from boldface B into 0 infinity be a regular Borel measure. Regular Borel measure with support, because it's a regular Borel measure on a locally compact T2 space, so it must have a support. और यहाँ वो support के बारे में हम assume कर रहे हैं with support of mu equal to x. So support is x. और हमने ये देखा if the support is x, then two continuous functions will be equal AE if and only if they are equal. ठीक है, तो वो चीज़ यहाँ होगी. असल में आपको मैं जो ये assumptions है हर एक assumption की implication बता रहा हूँ. हम ऐसा क्यों ले रहे हैं? Because everything जो आप यहाँ ले रहे हैं ना ये assumptions में everything has a consequence, और वो चीज़ हमें actually चाहिए आगे जाके. Support mu equal to x. Then by this symbol, by c of x, actually we use this symbol c sub c. c और सबस्क्रिप्ट में छोटा सा c, यही हम करेंगे. This is the standard symbol c sub c of x. We shall, ये ध्यान से देखिएगा कि इससे हम किस चीज़ को डिनोट कर रहे हैं. We shall denote the collection of all possible continuous functions defined on x having a compact support. Having a compact support. Full stop. और ये जो इसकी डिस्क्रिप्शन है ना, ये सिंबल की जो डिस्क्रिप्शन है, इट जस्टिफाइज द सिंबल. दिस सी इट स्टैंड्स फॉर कंटिन्यूटी, क्योंकि इसमें आप ले रहे हैं कंटिन्यूस फंक्शंस डिफाइंड ऑन एक्स. दैट इज़ द रीज़न आप ये एक्स देख रहे हैं यहाँ. और ये छोटा सा जो सी यहाँ आप देख रहे हैं, इट एक्चुअली reflects this. The functions which we are taking in this collection are having a compact support. So we are only selecting those functions which possess a compact support. और ऐसा क्यों, वो मैंने ऊपर पहले ही आपको दिखाया. Because whenever the function has compact support, it's an integrable function. In fact यहाँ कुछ और भी true है, वो भी आप यही से देख सकते हैं. ये inequality जो अभी हम देख रहे थे ना, इसको देखिए आप, इसे देखिए आप. मैं फिर से ये इनइक्वालिटी ले रहा हूँ. यहाँ मैंने आपको दिखाया था दैट 0 इज़ लेस देन और इक्वल मॉडुलस ऑफ f इज़ लेस देन और इक्वल m टाइम्स chi sub k, where k is the support of f. ठीक, and we are assuming the support is compact. If this be the case, then mod f raised p, it will be less than or equal. Basically, if you have to raise p throughout, यहाँ 0 है तो it will be 0 raised p which is 0, but यहाँ क्या होगा, it will be m raised p. Now what is m raised p times chi sub k? It's again a stuff function. Again a stuff function means an integrable function. 0 is an integrable stuff function. So again we have a scenario where this measurable function is squeezed between two integrable functions. So that means it must be integrable. So mod f raised p is integrable. Now it's integrable, it means what? It means f belongs to LP. It belongs to LPX. और b की s की जगह क्या है यहाँ पे, सिमरिंग की जगह है, यहाँ बोरल सिग्मा अलजेब्रा, और म्यू की जगह म्यू ही है. सो दिस f belongs to LP. The question is for which p? The answer is for every p in 1 infinity. इनफैक्ट यहाँ आप इन्फिनिटी भी ले सकते हैं, बट चूँकि वो चीज़ मैंने अभी आपके साथ डिस्कस नहीं करी है, तो फिलहाल हम इतना ही लेंगे. फॉर एवरी पी इन 1 इन्फिनिटी. सो बेसिकली ये होता है एक्चुअली, एवरी कंटिन्यूस फंक्शन विद कॉम्पैक्ट सपोर्ट ऑन अ लोकली कॉम्पैक्ट टोपोलॉजिकल स्पेस विद अंडर अ रेगुलर बोरल मेजर इज an LP function, and it's true for every p in 1 infinity. In fact, it's true for infinity also. बट व्हाट इज़ एल इन्फिनिटी, वो चीज़ चूँकि अभी मैंने आपके साथ डिस्कस नहीं करी है फॉर्मली, तो फिलहाल वो चीज़ मैं यहाँ क्लेम नहीं कर रहा हूँ, मैं बस इतना कह रहा हूँ. ठीक है, अब वापस आप यहाँ आइए. बाय दिस सिंबल वी आर यूजिंग दिस सिंबल टू डिनोट द कलेक्शन ऑफ ऑल पॉसिबल फंक्शंस विच आर कंटिन्यूस एंड हैव अ कम्पैक्ट सपोर्ट. और यहाँ जो आपने अभी यहाँ देखा, व्हाट कैन यू टेल मी इन द लाइट ऑफ दिस ऑब्जर्वेशन? ऊपर वाली चीज़ को अगर आप यहाँ इनकॉर्पोरेट करेंगे, सो यू कैन इमीडिएटली सी दैट. वो यहाँ से एक इमीडिएट रिमार्क फॉलो होती है, वो ये है, ये जो कलेक्शन है C sub Cx, where x is locally compact T2 space, this is contained in LP x B mu, where B is the Borel sigma algebra of x and mu is regular Borel measure defined on this Borel sigma algebra. Okay, so this is contained in this, and it is true for all the p's in 1 infinity. फिलहाल हम यही ले रहे हैं 1 infinity, open at infinity. ये चीज़ यहाँ मैंने आपको दिखाया था, this is a normal linear space, there is a norm on this. ठीक है, and now that this being a part of this, तो वो norm को आप इस पे भी restrict कर सकते हैं. And by the way, ये जो है, this is also a linear space, it's a vector space, because sum of two continuous functions is a continuous function. Sum of two continuous functions with compact support is a continuous function with compact support. Likewise, scalar multiple of a continuous function with compact support is a continuous function with compact support. ये मैं आपके लिए exercise छोड़ रहा हूँ. You check this, that this is a subspace. It's a vector space. This collection, ये जो है ना, it's a vector space over R. ठीक, तो मैं ये आपके लिए एक्सरसाइज रहेगी, आपको चेक करना है कि दैट इट्स अ वेक्टर से, और इसमें आप बस यही दिखाना है आपको. सम ऑफ टू कंटिन्यूअस फंक्शंस विद कॉम्पैक्ट सपोर्ट इज अ कंटिन्यूअस फंक्शन विद कॉम्पैक्ट सपोर्ट, एंड स्केलर मल्टीपल ऑफ अ कंटिन्यूअस फंक्शन विद कॉम्पैक्ट सपोर्ट इज अ कंटिन्यूअस फंक्शन विद कॉम्पैक्ट सपोर्ट. अगर आपने ये दो चीज़ें करी, एंड दिस इज़ क्वाइट ईजी, कोई ज़्यादा डिफिकल्ट नहीं है, सो दिस विल बी अ सबस्पेस. ठीक है, सो मैं एज्यूम कर रहा हूँ कि आप कर पाएंगे. अब जो मैं कह रहा था, फिर से आप उसी पे आइए. इस पे एक नॉर्म है, दिस इज अ वेक्टर स्पेस एंड इट इज कंटेन्ड इन दिस. नाउ इफ यू रिस्ट्रिक्ट द नॉर्म ऑफ दिस ऑन टू दिस, यहाँ भी आपको एक नॉर्मल लीनियर स्पेस मिलेगी. सो यू कैन सी दिस C sub Cx as a normal linear space also, because it's contained in LP and it's true for every p. So you can see this C sub Cx with the, if you restrict the LP norm to this C sub Cx, then this becomes a normal linear space, and it will be actually a subspace. This is a subspace of this bigger space, LP x B mu with the LP norm. So it's a subspace of this. अब ये जो स्पेस है, ये हमने देखा इन द रीस-फिशर थ्योरम, दिस इज कंप्लीट. We know that this space is complete, and that is the Ries-Fisher theorem. Now the question is, what about this space? ये space जो है, this is complete by Ries-Fisher theorem. Now what about this space? ये आपको पता होना चाहिए. In general, this space, मैं generally कह रहा हूँ ना, general, because we are dealing with, यहाँ जो ना, we are in generality. यहाँ कोई particular situation हम examine नहीं कर रहे. You are examining a general situation, so you have to speak generally. And in general, ये जो स्पेस है दिस इज नॉट कंप्लीट, और ये आपने देखा भी होगा इन जनरल दिस स्पेस this is not complete, generally speaking. और ये चीज़ आपने देखी होगी, आपको पता है, if you consider CAB with the sup norm, it's a complete space. But when you consider this with the integral norm, it's incomplete. So there is an example where this is incomplete. So generally speaking, this is not complete. So in general, this, although it's a subspace of this, but generally speaking, this need not be complete. Now this need not be complete means the completion, the question of completion becomes relevant. Now we ask ourselves, what is the completion? Every incomplete space has a completion. Now that in general the space is not complete, now the question जो यहाँ राइज होता है वो ये है कि what is the completion of this space? इसका completion क्या होगा? And the answer to this is, it's actually this space. This space is the completion of this space. और यहाँ से आप मुझे अब बताना, you should be able to tell me what will be the completion of CAB with respect to the integral norm. If you take CAB with CAB and if you consider this norm, wherein the norm of function f, where f is coming from CAB, is defined like this. If for f in CAB, if you define this symbol like this, और इसके नीचे मैं यहाँ 2 रख रहा हूँ और वो थोड़ी देर में आपको समझ आएगा क्यों. If you define this symbol as integral a to b modulus of f square dx whole raised 1 by 2. If for each f in CAB, if you define this symbol like this, you can see that this actually defines a norm on CAB. However, this CAB together with this norm is not a complete space, and the completion will be L2AB. Similarly, if you take CAB with this, instead of using 2 here, if you use P, it will still be a norm where P is greater or equal to 1. If basically मैं आपसे ये कह रहा हूँ, if you define this function again for f in CAB, if you define this function like this, integral a to b mod f raised p dx, यहाँ dx इसलिए ले रहा हूँ because it's a continuous function. Continuous functions or finite intervals are Riemann integrable, so I can take the Riemann integral whole raised 1 by p. अगर आप ये function consider करेंगे, so again you can see that this function is a norm on CAB. So CAB together with this function is a normal linear space, and it's an incomplete space. It's not a complete space. और इसका जो completion होगा, that will be LPAB. और यही मैं आपको दिखाऊंगा. In fact, इसको दिखाने के लिए मुझे बस ये दिखाना है that the completion of this space is this space. If I somehow show that the completion of this space is this space, we are done. यही से फिर follow होगा that the completion of this should be LP. Obviously, this P has to be greater or equal to 1. Otherwise, this won't be a norm. यहाँ triangle inequality में मसला होता है फिर. If P is less than 1. ठीक है? So our main objective now is to prove that the completion of this space is this space. ये मैं आपको दिखाऊंगा अब. इसमें मुझे बेसिकली अब कल हम करेंगे. ये एक ठीक ठाक इसमें ना कंटेंट है ये रिज़ल्ट में, बट इसके लिए कुछ चीज़ें मुझे चाहिए, वो मैं आज ही आपके साथ मैं अभी वो निपटाना चाहता हूँ उन चीज़ों को. आप सबसे पहले कल मैंने एक रिज़ल्ट आपको दिखाया था जहाँ मैंने आपको दिखाया था कि दैट द कलेक्शन ऑफ स्टफ फंक्शंस इज़ डेंस इन एलपी. मैंने आपको दिखाया था इफ़ यू टेक अ फंक्शन एफ, ये मैंने आपको कल दिखाया था. इफ़ यू टेक अ फंक्शन एफ इन एलपी एक्सेस म्यू, then for each epsilon greater than 0 there exists a stuff function phi sub epsilon such that integral over x f minus phi sub epsilon mod raised p d mu whole raised 1 over p, this will be strictly less than epsilon, and this actually is the LP distance between f and phi sub epsilon. ये दिखाया था मैंने आपको कल, and this is true for all the p's. This is true for all the p's in 1 infinity. So in particular it's true for p equal to 1 also. That means if you take p as 1, so you are basically speaking about L1 functions. L1 functions means integrable functions. So every integrable function can be approximated by a stuff function to any degree of, you can actually achieve any degree of closeness in this approximation. Because every LP function, so in particular every L1 function can also be approximated. ये देखा था हमने कहा. और यहाँ जो approximation के लिए आप इस्तेमाल करा, you are using stuff functions. Now what I am telling you that you can also use special stuff functions. ये पहले आपको पता ही नहीं होगा कि what is a special stuff function. तो ये पहले आप definition आप रिकॉर्ड करिए. Special stuff functions. Special stuff functions. Special stuff functions. Let excess mu be a major space and phi from x to r be a stuff function. Full stop. Now if phi equal summation I runs from 1 to n ai chi sub ai be the standard representation. We know that every stuff function has a standard representation. तो ये मैं ले सकता हूँ. मैं यहाँ मान रहा हूँ कि this is a standard representation. Be the standard representation of phi. Then this phi is said to be a special stuff function if and only if. देखिए इसके लिए क्या रिक्वायरमेंट है. if and only if एक सिंपल सी रिक्वायरमेंट है इसके लिए, और वो ये है ये जो लेवल सेट्स आप ये स्टैंडर्ड रिप्रेजेंटेशन में देख रहे हैं, these AIs, they must be coming from the semi-ring. This is not necessary for a general stuff function. ये है requirement. These AIs, they must be coming from S, the semi-ring of the measured space, and this should be true for all the I's from 1 to n. मतलब for every, जो भी आप यहाँ ये level sets देख रहे हैं ना standard representation में, ये सारे level sets semi-ring से आने चाहिए. अगर ऐसा है, we say the stuff function is a special stuff function. ठीक है. स्टफ फंक्शन होने के लिए ऐसी कोई रिक्वायरमेंट नहीं है दैट द लेवल सेट्स शुड बी कमिंग फ्रॉम सेमी-रिंग. हाँ, अगर वो लेवल सेट्स जो आप स्टैंडर्ड रिप्रेजेंटेशन में देख रहे हैं, अगर वो सेमी-रिंग से आ रहे हैं, देन योर स्टफ फंक्शन इज कॉल्ड अ स्पेशल स्टफ फंक्शन. दिस इज द डेफिनेशन. मैंने रिकॉर्डिंग करी है इसकी, नोट्स जो आप कह रहे हैं ना, मैं डायरेक्टली इसकी वीडियो रिकॉर्डिंग आपको दूंगा. ठीक है. अब ऊपर जो है ना, अभी आप यहाँ, ये कल मैंने आपको दिखाया था दैट द कलेक्शन ऑफ स्टफ फंक्शंस इज डेंस इन LP फॉर एवरी P एंड देयरफॉर इट्स डेंस इन L1. The question is, what about the collection of special stuff functions? Obviously, not every stuff function is a special stuff function. Because जब आप standard representation की बात करते हैं, the level sets may not be semi-ring elements. So not every stuff function is a special stuff functions. If you consider the collection of all the stuff functions, it is dense in L1. But when it comes to the collection of special stuff functions, since it's a sub-collection of the collection of stuff functions, the natural question which arises here is whether this sub-collection is also dense, and the answer is yes. ये आपके लिए exercise है, और इसका जो solution है ये आपको मिलेगा जो हमारी वो जो टेक्स्ट बुक है ना, इसमें CD Libranthes की, उसके एक मिनट में आपको बताऊंगा ये कहाँ मिलेगा. ये कोई 2-3 लाइन्स में ये आप ना इसको प्रूव कर सकते हैं. ये शायद थियरम 25.3 के कुछ, एक सेकंड कंफर्म करके बताऊंगा आपको. हाँ सॉरी, 25.2 है ये, थियरम 25.2 ऑन पेज 201. अगर आप वहाँ देखेंगे तो वहाँ से आपको इसका सोल्यूशन मिलेगा. तो मैं ये आपके लिए एक्सरसाइज छोड़ रहा हूँ. इट्स एन ऑप्शनल एक्सरसाइज, अगर नहीं भी करेंगे तो से आपका जो ये कोर्स कंटेंट है उस पर कोई इम्पैक्ट नहीं पड़ेगा. शो दैट द कलेक्शन, और मैं आपके लिए थोड़ा सा काम यहाँ आसान दे रहा हूँ क्योंकि आप जो सोल्यूशन में भी वही है, वहाँ उसने खाली L1 को लिया है, सो वही मैं आपके लिए दे रहा हूँ एक्सरसाइज. शो दैट द कलेक्शन ऑफ all possible special stuff functions or measure space axis mu is dense in L1 axis mu. That means every integrable function can be approximated to any degree of closeness by a special stuff function. This will be an exercise for you. इसको देख लीजिएगा, बाकी मैं कल ही आपको बाकी इसके बाद जो है वो खुद ही बताऊंगा सारा. मेरे ख्याल से काफ़ी आज के लिए, क्योंकि अभी लेट भी हो गया, तो बाकी इंशाल्लाह कल देखेंगे. कल से आपकी क्लासेस ना थोड़ा, असल में मुझे आज यूनिवर्सिटी जाना था तो एक मिनट पहले ये रिकॉर्डिंग में स्टॉप करना.